Okay, John's going to continue.
We're gonna start? Okay. Okay, so I'm gonna tell you, I'm gonna do a little drill on the math. So the first part of the math is sort of old control theory, but applied to kind of new problems. And then the last half is new control theory in its simple, but in its simplest possible form. So I want to look at some simpler examples. So we can't do that, but we have these VR versions. But we're gonna do some new stuff. Okay. So let me get up, maybe get over there. So we're gonna do some new stuff here. Okay. And so what we're going to do is look at this text. Oh, this isn't working. Shit. Okay. You're not to be supposed to read this. The problem is we're getting. So this is an example of where the sync is not working, and so you're not supposed to be able to read this. At 2 hertz, it's too blurry. Okay. But it's getting. It's
harder to read than the stuff on the upper left.
Yeah, a little harder. Yeah. Okay. But if you shake your head,
I can imagine.
Shake your head, you can't read anything, right? No, sorry, all the way around. If you shake your head, you can read everything, but you wouldn't have been able to read this, even though you can shake your head a lot faster than 2 hertz. So here's a way to do it. Okay, take your hand and do this, and it blurs, right? Okay, do that, and then put it here and shake your head, and it doesn't blur. Okay, okay, and you all know why. Right? It's because of this system, and I'm just saying about that. So why do we have this? We used to have to do this. We had to run down these guys. And so what you need is, if you were here yesterday, speed accuracy trade-off. You want to be fast, flexible, and accurate. You don't have a part. You do this with that, and you do that with this. Okay. This vestibular books. Everybody knows this, so I'm just reminding you because we're going to do some more stuff. So the idea is that this is the way the object motion works. It goes through vision, and there's a big delay here, and then it acts on the eye. Okay. This has got low delay. VOR goes directly to the actuators, and through the ear a lot faster, but not very flexible. Okay, so you're actually using vision to read this, which it wasn't evolved to do particularly, read PowerPoint slides, but you're reusing it. So okay. Okay, so this is a layered architecture. You have a layer of object motion on top of a layer of head motion. This is sort of this is a reflex. It's one of the fastest reflexes. So what ends up happening for this job, for the running around and hunting on the savannah, this is a sweet spot because we end up having is fast, accurate, and flexible, even though you don't have any part that is, you got these 2 other parts. Okay, story. Okay, so you've seen this. Okay, so what are some of the trade-offs? Okay. So we talked about this yesterday. Okay, so I'm gonna skip this. So what are you really doing here? So there's three layers. So if I'm now balancing myself, okay, I'm moving around, I'm balancing myself, I have 3 layers. I have proprioception, I can feel. I have the vestibular system, and I have vision. Okay. So now we're gonna balance me and a challenger who's going to demolish me. So this is the system. Now we're talking, we've got cerebellum, the vestibular cerebellum. I'm sure you know all this, vestibular nuclei, reticular formation, then you got the muscles and the balance. Okay, so you know this a lot better than I do. I just said a bunch of things. I have no idea what I'm talking about. It's just a bunch of boxes of control there. So I know what math I would put in those boxes. So anyway, okay, and this is how we balance. Okay, so what happens if we remove vision? What's going to be the prediction? If we lose our accurate sensor, what's going to happen? Fall down. What?
You're blind.
Yeah. Okay, so I turn my vision off. What's going to happen to me? I'm going to run into things. Right? Okay. But I can scale balance. Why? Because I have good proprioception and I have this thing. So I'm not going to fall over. Okay. Okay. Now what happens? I'm going to degrade my proprioception.
Okay.
I'm going to stand on one leg.
That proprioception, but you can't stand.
So now I can stand on one leg. Not very well. And you notice that, okay, now I'm going to do both. So this is the interesting part. If I do this, what's going to happen is I'm going to do this, and then I'm going to close my eyes.
You might fall.
And I will fall. And notice I oscillated before I fell. That oscillation has no purpose. This is an oscillation with purpose. That oscillation is a sign of that. Okay. So I do that, and then I fall over. Okay. So anybody want to do this with me? Okay. So let's see what happens between a young, fit, healthy, young person.
I'm a bit hiking now, I'm a bit tired.
Okay, so we're gonna both do, we're gonna, and so 3, 2, 1. Oh, sorry. So we'll stand on one leg.
Okay.
Okay, well, okay, and then close your eyes. Okay,
Much better.
much better, right? So you want to know, okay, you can stop. Okay. I'm now sufficiently, I'm sufficiently humiliated, okay. And here's the really, really bad news for me. So there's all these behavioral, or there's all these biological markers that are very predictive of how long you have left to live. One of the best ones is the one we just did. So, okay. But what happens if you do this? You want to try this?
Yeah, sure.
Okay.
Let's do it.
Okay.
I don't know what we're doing, but.
You're gonna just spin around as fast as you can.
Ooh, I'll vomit. Yeah.
Oh, you will?
Yeah. This
Okay, Linda,
I'll
you
try,
can.
I'll try.
Okay,
That's the fourth box, John.
Yeah, this is the fourth box. This is why I study prediction errors, because I.
No, it's we're gonna degrade the vestibular system by spinning.
Okay.
You want it? I can do it, but you can.
I'll watch you do it first.
Okay, so I'm gonna go.
All right,
Okay,
okay.
so you have to, sorry, you're degrading this too.
It's a book. Okay,
Okay,
so you want me to
well,
spin? Yeah, I need the animation.
Okay. Yeah, so you degrade, okay, so I degraded my outputs, okay. So anyway. Then you hold it. Sorry. Why motion sickness? Okay. So why motion sickness? And I'm just, so what happens is, really, so this is, it turns out, this just happens to be the most sensitive poison sensor in your body, okay? Wasn't designed to do that. It just, you have to match, you have to fine tune, because this is, you can't do this genetically. You have to actually fine tune this. You have to learn to do this, right? So this is the place where you tune, because you got to match this with this. There's no reason those gains should match, okay? Because you have to work through the same actuator, okay? So that's it. So what happens is, this is the system you were doing, but the idea is that what you just connect this thing up to is you throw up. Why is that? Well, this is a good poison sensor. So before you feel you're sick, you get nauseous and you throw up. It's because of this system. So you're just hijacking, in a good way, an existing system. So you're in another layer of control on top of the existing architecture. And then it does all these other things. Okay, so that's a very sensitive sensor. So you need a sensor that's high and fast. So why is it important that my eyes are in my head? Okay. So now we're going to switch to this. So now we're going to balance this instead. And I can balance that a lot better. Okay. So how does this work? So there's basically a universal law, and that's this law. This, I keep telling you there's these universal architectures. This is a universal law, applies to everything. Okay. We'll talk about it in the context of balancing a state.
And tell us what the variables are.
What?
He doesn't like to do that.
Yeah, you're gonna do that. Yeah, we're gonna do that. So here's one of the things is, so this is easy. This gets hard. And this gets a lot harder.
Yeah, but you know what's interesting? It only goes as the square root of the line, the difficulty. In other words, your speed only goes as the square root. If you work the dynamics out,
I remember.
yeah, it's the square root of the line.
Okay, so we'll get to the formula. So then what's interesting is, so that was hard. But this is easy. But now if I look down and occlude my vision, it's completely hopeless. So at a length that is easy, it's hopeless. So why is it so much harder to do this than this? Okay. So here's the idea is, oh yeah, there's your square root. Okay. I didn't know that.
But what's P there? What's the meaning of this?
Please define all the variables.
Okay. Yeah, okay, so,
Stickler, but
oh yeah, that's another thing. So I'll tell you what they are. Okay. So this is the length. So this is the length. Tau is the time delay in your visual core, through vision. So it's,
Yeah.
right? Time delay. And P is the pole location of the instability, okay?
Whole
So-
location.
So this is an unstable pole, so it goes like e to the p. So
Oh, yeah.
this goes like e to the pt, right? It falls over e to the pt, and then I just plug in the delay and I get e to the p tau.
Sorry.
But the thing is about this, that the P increases the, this is the time constant increases exponentially with the angle.
No. The exponential increases exponentially with the t. Okay.
Okay, right.
Okay.
Okay,
And what is p? P is proportional 1 over the square root of the length. So as the length goes down, this thing gets more and more unstable. So here it's pretty slow. Here it's really fast. Okay. Yeah.
So I didn't really get this. So exponential p tau is what? It's like the
So-
deviation from straight up
So if I let it go, it falls away exponentially fast
in time.
in time.
Okay.
And that would be e to the pt, where t is just time falling over. Okay. Tau is your delay through your head. And I just plug that in and I get this curve, and that's exactly what happens. Okay, and it's on a log.
Curve is length on this x-axis.
What?
and-
It's the length.
What is Y?
Y is this. It's how bad this is. So this is just a measure of the error. You can measure it in 2 ways. You can do it sort of entropy or worst case norm. Okay. So this is just how hard it is. Intrinsically hard. Okay. And it says, whatever control you have, if you got this much delay, this is how hard it is.
Yeah, okay, but since this is a bit of a tutorial,
Yeah.
and this is a way to measure control performance or robust.
This is 2 ways,
Two metrics.
2 different metrics for control performance.
Or what? What does it measure? How upright?
This measures worst case disturbance rejection. And this just is sort of an entropy measure on how much the signal looks like.
So what's capital T?
Oh, I didn't tell you about that. That's the transfer function from disturbance. So if I'm sitting here, there's a little bit of noise in my vision. And it's how much does that noise get amplified to the error?
The magnitude of this transfer function, the maximum magnitude of the transfer
Yeah.
function, the disturbance.
Yeah, that's right. That's right. And it scales like this. Well, it scales like this when I'm looking at the top. And it scales like this when I'm looking down here. So I got to tell you what these things are. Okay.
So
So now here we got the P. P is the instability, which goes like 1 over the square root of L. So Z is the location of a 0, and it scales like, I think it also scales like this. So what ends up happening is, as Z gets small, no matter what P is, this gets much worse. Okay. So as Z gets small, this thing gets much worse.
That's Z of the Z transform.
Sorry, as Z gets big. No, Z is at the Z transform. Z is the location of the 0 in the transfer function. Yeah.
0 meaning the low high pass corner.
Yeah. Yeah.
I mean, so
So this is why, let's go this curve. It's exponentially worse than this. So this is on a log mod. So this is enormously harder than this. This is not that hard. This is completely hopeless, and this theorem says why.
But
Yeah.
what's the intuitive reason for that? It's because the pole rotates around that point, so you don't get information.
Well, here's some intuition. So here's the way of intuition about it, right? So when I'm here and it falls, I've got to go all the way out and catch it, bring it back, and do that whole maneuver. So watch me if it falls, I have to go out. So notice I'm going way further out. This thing isn't moving much, right? This isn't even moving much, but I'm moving a lot, okay? Now the problem is, when I'm down here, it all goes the wrong way if I go below the center mass. So you're getting really bad sensing, and no matter how smart you are, you can't undo that sensing. It's a little bit like if I drive forward into a parking space, okay, no big deal. But if I drive backwards, I go way outside. I go in the opposite direction from what I want to go.
so I mean, are you saying that the ideal controlled trajectory would be proportionally smaller when you have a shorter stick, and then
No. It just means no. Well, now notice I'm working a lot harder here, right? I'm really working hard. It's more that I have to get faster, not that I have to get bigger. Here I can be kind of slow, right? It's not that I'm moving bigger, just I'm moving slower.
Is the house not function of the mass of the top?
Doesn't matter.
For Ron, it doesn't matter what the mass is.
Yeah, well, actually, if the mass is distributed, it matters where the center of mass is.
Yes.
And so this is heavy enough that that's. You're right, it's the center of mass. Yeah, this is gonna be a lot harder. Yeah, this is like, this is hopeless, because the center of mass is down here, that's really good, okay, so.
No, but that's exactly consistent with the theorem.
And you can do that all with the theorem, yeah,
That's the same thing as looking at it at the bottom.
yeah, exactly, yeah.
Exactly.
So anyway, so I don't want to spend too much time on this, because this is like undergrad stuff that's like 20 years old, but I just, what I want to tell you is, this law applies to everything. So there's functional reasons for us to have oscillations all over. Wheels, walking, as Carrie does, the wheel. Anyway, so we have oscillations, we have radio waves, we have oscillations all over that are functional. This oscillation is a fragility that's unavoidable, okay? I don't want it, I just would like it to be like this. I want it to be like that, but I can't avoid these oscillations because of this theorem, okay?
Right, but does the theorem determine what is your sample rate that you need for a certain?
That would be go into tau. If you're building, if this wasn't your brain gives you tau, but if this was your robot, tau is determined by your electronics.
Yeah, but once you know what that delay is in the perception, then
The point is, any control design you do, no matter how optimal, is going to be stuck with this trade-off. This is for all possible control systems. It's a law.
trade-off which says that the maximum disturbance or the.
It's going to be this bad, no matter what you do. So it's a law. Okay. Okay. So anyway, that's why.
So how do you prove it?
So why oscillations? So oscillation, this oscillates, right? This oscillates because of what? Gravity and classical mechanics, right? This oscillates, okay, so this is mechanics, gravity, and light, plus this thing. So this is a law like these are, okay? And everybody kind of knows this, and like nobody knows this because we teach it badly, me included. Okay, and the point is, I don't care what you put in this box. If you got this delay, you can put any optimal control in this box, and you are stuck with this trade-off.
Is your T the transfer function of a linear system?
Yeah, so T is the transfer function. If I have a disturbance in my visual system, a little noise in it or something, it's the noise to this error, and that's what we call T. It's a linear transfer function. So this is the linearized equation.
That's a key point here.
Yeah, it's a linearized equation. We can this generalizes to nonlinear. It's not a big deal, but we don't really need it here. And the tau here is maybe 300 milliseconds because you have the whole visual system, and then you have the actuation. Okay. Okay. So you have the stable. This is stable. But I can do like easy, right? This is stable, but I got to pay attention. And here's an example of what can go wrong. This is normal blood sugar, and this is blood sugar roller coaster that's caused by degradation in your control system.
What kind of degradation in this case?
That's another hour.
Okay.
This is an airplane. It oscillates before it crashes. Okay. Power grid, glycolytic oscillations. Yeast glycolysis oscillates. Okay. Why? No idea. So, no idea. You can make simulations and you can make yeast extracts, and they both oscillate. So you have a model of what happens, but the question is, why would evolution ever evolve to have this stupid oscillation? So what's the function of this oscillation? Well, it turns out there's no function. It's just the same damn thing. It's just the same thing I just talked about. Okay.
But isn't it the symptom of having to regulate things by feedback control?
Yeah, if you don't do that, you die.
Yeah.
Okay, so this is like death. I don't have to do anything. This is like life, and if I don't control it actively. And the problem here is, where's the source of instability here? It's autocatalysis. You have to run this thing autocatalytically. You've got to use ATP to make ATP. You can't avoid that. All of biology is autocatalytic. That makes everything unstable, and you have this problem. Okay. So this is all over. And the point is, you have these laws, and you just say you can't blow this, and this is one of those laws. Okay, this is what the reviewers said. Simply wrong. They said, there's too much diversity in such systems. I'm going, that's all I talk about is diversity. Sorry, okay. Doesn't understand this, well, you know, anyway, these are the reviewers. So we're saying diversity implies architecture, right? That was what I've been talking about all these times. So this is diversity implies no architecture, so reject this crap. But then you get reviewers like best paper I've ever reviewed in this subject. And so what does the editor do, right?
Yeah.
So it finally got published. But the editor went to the editor-in-chief and got reviewers to review the reviewers. Right? It finally got published. But usually this happens and you just, you know, you get triaged if you're NIH. And if you're Nature, they don't even look at you. So this was a miracle. I had an unbelievably good editor here. So I just want to say thanks in that case. And that's in this book, and this book is from like 1988. So all this stuff. Okay. So here's other examples. This is like death. Very stable. Okay. This is like life. Stable, but fragile. And we just talked about the EBOs last night. You can imagine what goes over here. Okay. So this is that picture. Okay. So, okay, end of that. That was just, that's sort of what you can say about these systems using, oh, so I don't want to do that.
Say, right?
Okay. Okay, so all I'm saying is that this is the first of a long list of laws that biology has to obey in addition to physics. Okay. So I've just given you one. We could spend lots of time giving the others. I'm going to switch to a little something different. So I'm going to share. Yes.
John, what's the origin of that universal law? Is it something to do with fluctuation dissipation type of thing? Or
No, it's not. But if you know this, you can actually prove the fluctuation dissipation rigorously, which isn't done in StatMech. So you can, if you know this stuff, you can fix StatMech, but it's related, but no. This is originally due to Bodie in the 40s. And we did some refinements of it in the 70s and 80s. So yeah, no, interesting question. So now up to date. Okay, so okay. The problem with biology. So one of the problems here, what makes this hard is because I'm slow. Okay. And so if we're doing this with all electronics, I don't have as big a problem as I would with myself. Okay, so the problem we have is I had a delay, and that delay made this problem hard for me. Okay, if I was a lot faster, it would be easier.
Can I ask about that? So you're 300 milliseconds, you said
Yeah.
it's the sentiment delay and then like the actuator delay.
Yeah, total delay.
Like, is there, I mean, you do still have like a forward model here, right? So is there like a, a delay calculation cost of
Yeah,
computing?
it's around the
function to control.
So experimentalists tell me it's around, the total delay is around 300 milliseconds.
Right, but you seem to be excluding any cost due to the actual computation of your control solution.
That's included in that.
That's included in the
Yeah.
actuator.
Yes, it's all the total delay from sense to act.
But is that not variable? Is it like a computability problem there about how long it'll take to compute?
That's included. Now, there's individual variability. So some people are 250, some people are 350, some people like take forever. So some people can't do this at all. So one of these you can't, if you don't have binocular vision, you can't do this at all. So I'll close one eye and it's hopeless. So there's a whole bunch of stuff. We can add details endlessly, but I'm going to switch. Now what I want to talk about is let's zoom in on these delays. Where do these delays come from? And how does our brain compensate for them? So what's going on internally to deal with these delays? So actually you're anticipating the next okay. So the thing is, how does our brain actually have to do this? Well, it's got computers all over the place. It's got sensing and actuation, but there's delays everywhere inside our system. Okay, so we talked about this picture for the biking game, but the idea is that you really have this problem and not that problem. So let me try to say, what's the theory for this? When our old theory was this: cheap, fast electronics, you just speed of light everything, you just put everything in, you put everything into one computer, maybe quad redundant, but you're so fast, so you're doing speed of light and this is speed of sound. orders of magnitude difference, nothing to worry about. Delays are not a big deal. Okay.
Well, that's not really true. I mean, for example, you take a small robot with limited computing. Yeah. That's a claim.
You can make up robot problems where it's hard. Okay. But take this guy and it's like this. And if you're sparse, delayed, quantized, and sensing, communication, computing, and actuation all the way through. Everything is delayed, everything is sparse, everything is quantized all the way through. Okay. Okay. So instead of this, you got this problem. You still have centralized control, but the lower layers are all distributed and localized delays. Okay. And so this was the hardest problem of control theory until 10 years ago. And if you know Witzenhausen, that's the name that goes with that order. So that's what we want to work on, which is how do we actually implement the bumps layer? Okay. Okay, so everything's sparse and delayed. So what you have is you have these layers. You have a compute layer, you have a communication layer, you have a sense and actuation layer, and then the physical plan you have to do. And everything's delayed all the way through. Okay.
What's sparse here?
Everything.
Everything is sparse.
We're not seeing where the plant is, but everything here is sparse. You don't have all-to-all connectivity anywhere. Everything is sparse. The actuation and sensing is sparse. You don't get to actuate and sense everything. The communication is sparse. Your computers are sparse. Everything is sparse. Okay. So that's not sparse. That's dense everything. Okay. Okay. So this is the problem we have, and this is what needs system level synthesis. And this is completely intractable until like 10 years ago. So what we're going to do, here's our strategy. We want to do the following. We want a theory that lets us think globally and act locally. So what we want to do is design and implement patches, but do so in such a way that we come damn close to what we would have been able to do if we had a centralized controller. That's what we wanted. And that was hopeless. Okay, so we're going to zoom in a bit. So I'm going to make a little picture here, which is just a 1D system. So this is the physics down here. We'll go through this a little bit. And then all these boxes are bits of electronics or computers. And then these are the highest layer computer. And so what we have here is we have actuation in red, sensing in blue. So sensing is less sparse than actuation. So I can look at everything in this room, but I can't touch it without a lot of delay. Okay. So if I want to go over and punch Toby for being such a jerk, I'm going to have to walk all the way over there and punch him. So I can see him. So I can see that he's a jerk, but I have to go all the way over there to punch him. Okay. So, okay. And then there's communications between the computers.
Sorry, I can punch you for you if you want.
Yeah, what? Yeah.
I can punch you for you.
Oh, okay, okay, we're gonna get to that. So what I would actually want to do is have Shishi punch him. Okay. Which she probably has already done several times today. Anyway, okay, so there's delays everywhere, right? Okay. And so, but what you want to do is where do I get information from? I get information from my neighbor, but also I get information through the physics. Okay. So I want to see what that is. So we have fairly dense sensors. So we're going to simplify everything. Suppose we can sense everything for now. Okay. We can do sparse sensing too, but I want to keep it a little simple as possible. Okay. So we're going to take a matrix to describe this, and it looks like this. What does that look like? Does anyone recognize what this matrix is? Toplets. Yes. Okay. They're all over the place. So I'm going to make a ring of these things just to give you a feel for what the kind of dynamics are. So suppose you hit that place, and then you run it with these dynamics. And notice the discrete time, AX plus, and we're going to put control in, and then we have this disturbance. So this disturbance hits. What happens when that disturbance hits? Okay, so this is, I'm going to do a lot of these. So this is open loop. These are the 4 states, or 5 states, and this is time. So this is how this thing propagates. Okay, so let's look at this. Okay, hit there. You hit there, and time goes like that. So after one time step, you spread. Next time you spread a little further, spread further, and now you're blowing up and you die. Okay? So this is like everything blowing. So it spreads and blows up. Okay?
But these things have local feedback, so they're supposed to not blow up, right? Or what?
Not yet. This is open loop.
Okay.
So now we're just gonna make, you know, sort of, we're gonna make a long chain eventually at some point here. So we're just gonna look at this and put the space here, and then we're gonna do this, okay? So what am I doing here? I've got space here, I had an impulse here, and it spreads. And this is neutrally stable. So this is blowing up. You know, this is the whole power grid crashing, or some infection taking you down completely or whatever. Okay. So it's kind of neutrally stable. Okay, so do you understand? This picture is just a space-time picture. So time going this way, space going this way. And the reason I'm picking a 1D space is so I can draw it in 2D. Okay, so I'm projecting everything that's hugely dimensional into these low dimensions. Okay. So this is what we'd like to do. Why not? You need dense everything to do this. This is what we do in the aerospace industry, except when this is on Mars. But so we got to do this thing. So what we want to do is add a control. And so what are we gonna do? Let's just take, so what we're gonna have is a sensing actuation layer like this. Okay. And then we're gonna build sparse actuation, dense sensing, and then sparse computers. And there's a computer everywhere there's an actuator, because you got to put a lot of hardware in to have an actuator. It's cheap to build sensors. So everywhere you've had this, you have a computer. So now we're going to put the control in. Okay. Okay. So this is all just parts, and everything's delayed. Everything. Okay. So you can do this too. Okay. Okay. So we got this situation where, so we got this picture now. We're going to do this just in one dimension instead of, this is kind of a 2D plan. We're going to do this all in one dimension. Okay. And so, and this is our usual state space model. This is the model of the plant. What we have is we have a control action on that plant, and then we have some measurement, and it can be a sparse. If this is not the identity, it's sparse. We have perturbations here, and we have perturbations here. Okay.
Right, but A and B are matrices.
A and B are constant matrices. Yeah. Okay. Linear, simplest linear system. Okay. Now what I want to do is give you closed loop quantities. So this is X and U as a function of delta X and delta Y, okay? So delta Y is acting here, delta X is acting up here, and this is the closed loop map, and we're gonna call it RNML. This is just the closed loop system, that's all. We call it.
Why do you put delta X now? Oh, because it's differential.
X is the state, this is just a perturbation on the state. So what we're gonna do is we're not gonna design K, we're gonna design this. This is the big shift in this theory, which is, it turns out designing controllers in this setting is completely intractable. God awful hard, don't do it. And this thing is a god awful complicated function of the controller. It's actually a linear fractional transformation. It's not that bad. It's polynomial the controller. But we're going to design this, okay? And that's the huge shift in all of this. So we're going to just take simple state feedback. We're assuming we have the X. We know the X exactly. We have the disturbance, and then we have a control that the control is sparse because of B, okay? So that would be this picture. So what's going to happen? This is an intuition. So what do we want to do? Okay, we're going to assume that our communication is faster than the plan. Okay, 2 times faster. So intuition is I get a disturbance here, a state deviation. At the next time step, I know that. But at the same time, I propagate it to my neighbor. But my neighbor, surprise, right? Okay, the neighbor just got a surprise. So the neighbor now knows what happened, but I also got information here. Okay. So, but now we've got 2x the time speed. Okay. And so once we get out here, we can stop it. So you see it going, look out, look out, look out, look out, look out, and then somebody's coming going, boom. Okay. Easy idea, right? So what you need is to have this be faster than this. If this isn't faster, then we got another problem, and maybe I'll get to that at the end. So zoom into a patch. We want to do this and localize everything, okay? So we did. So if I get a disturbance here, I want to have 2 things happen. I want to stop its propagating, and I want to do it with just the neighborhood, okay? So 2 things. I want to keep it local, and I want to do it local, and I want to do it local in 2 ways. I want to design locally, and I want to implement locally. Okay. And it turns out that's a much easier problem if I enforce all of those things, which is what we want. So we were just asking a stupid question. Okay, so that's fiction, okay. So now what I'm gonna show you is how this kind of works. So this is open loop, okay? Neutrally stable. Can't do this. So this is what I would do with ideally, this is what this would do. No delays, perfect everything, right? What you do is you get this thing, you instantly act everywhere. Notice this is caused by your control, not by the propagation. And then you have exponential decay and it goes away. That's standard, that's what this controller would do, okay? Now what happens is we want to slow this down, okay? So we're saying, no, I can't act right away. I'm gonna have communication speed is about twice. I still do basically as well, okay? But our old control theory couldn't solve this problem. So that is the instant case. This is what the control acts like. So you get a disturbance, you instantly act everywhere. And you suffer this penalty elsewhere, but you kill everything quickly, okay? And we're going to call this just the patch R and this patch M. This is the closed loop behaviors, okay? So, and this is global into design and implementation, dense sensing and actuation, instant communications. Can't build this. Okay. So you can't do that. Okay. So what you do is you do this. So what this is, it's delayed and it's sparse, and the performance is inconsequentially worse. Okay. When I first saw this, I was going like, first of all, I said, it can't be that easy, right? I go, no, I go, I checked, I got to check too. Holy shit. You just got 5 paper prizes.
Are you saying, just so I slow you down a little bit, so are you saying that now you have a procedure?
Yes, it does this.
Algorithm that can generate this controller, which is basically the coefficients of these matrices.
The controller will be built out of this. So all I'm doing now is I have a way of saying what is feasible to do if I put these constraints on. What is possible? I haven't told you how to build a controller yet.
Yeah.
I can do that. I know how to do that. But notice what I've done is I've really drastically limited what the controller is capable of doing. And I've drastically limited the scope of this disturbance, but it's not much worse. It's like 2% worse.
Right, but what's the implication in R and M? R and M are matrices here.
R and M are transfer functions. They're impulse response.
They're impulse response.
They're impulse response.
I see.
Okay. That's what these are.
Right.
Okay. Right. So we can zoom in. And what you see is we're not actuating here, right? We're actuating strongly but locally, and there's a little delay. But this guy doesn't have to do much work now because they've done most of the work. And this guy doesn't propagate very far. Remember, it propagated quite wide. Okay. And the idea is that don't design K, design R and M. But I haven't told you how to do that, right? But it turns out this problem is convex in R and M.
But wait, what's a sparse impulse response like that? That's an impulse response in
the state space,
yes,
over time. So this says
so some that's locked at 0.
so this guy is acting on this state, but there's no actuator here. So this is just 0. But this state has something going on. Okay, and this is propagating, this dynamics is propagating, you can't stop that, but then we cut it off in time and space. This we care about, this we don't care about, this is just to simplify the diagrams. We could go this on to infinity.
So you want the sparsity downstairs.
That's because I can only have actuators here.
Right. But you want.
And then I want this delay to be manageable, I have to be able to do that fast enough.
Right.
And then I want to get this.
Right, so is this a correct interpretation?
Yeah.
You want to have sparse sensors actuating.
And sensors and actuators.
Sparse sensors, so downstairs, because they're looking at this fast diffusion upstairs. So you need to spread out the sensors.
No,
so that
we can't afford to put actuators everywhere.
I understand your cheat,
Okay.
but I'm trying to understand it theoretically. Because I'm seeing the top one still looks like a diffusion. It's an odd diffusion, but it still
Yeah,
looks
it looks
like.
like diffusion, yeah.
And so what you're doing is
You're limiting that.
you're limiting the diffusion by cleverly sparsifying where it's measured, right?
Where it's actuated. Yeah.
Where it's actuated.
That's correct.
Yes.
It's not a diffusion.
So we're localizing both.
Amplified diffusion.
So we're calling these patches, okay? So we design patches, okay? So the point is, how do we get a controller? That's the formula. So once I have M, I have this,
Yeah, it's 1 over diffusion.
right? So once I want K. Once I have M and R, it is convex in these guys. Then I just solve this to get K. What do I like about that? This is not sparse. The inverse of a sparse matrix is a sparse. I want a sparse implementation. I want K to be sparse. Okay. So it turns out you just implement it this way, and I'll show you what the diagram is. So this is all local. This is all. So now you're implementing directly in the variables, and so I can show you what the block diagram looks like. So this picture. Okay. Sorry. Let me just see if I'm not showing. Okay. Okay. So I have to get. So I haven't showed you what the meso circuitry is for the implementation of the controller. That's where the action is, and I'm about to get it. But so the idea is that here, let me summarize this. This is all instant, global, and you get this but this is instant. Here, you get this kind of process here, but you want this to be sparse, and this black is just where I don't actuate. Okay. Okay, so I'm going to draw it without the sparsity. Okay, so let me tell you how. So now I have to tell you how the controller is implemented. Okay, so this is where we started, okay? So what does the K actually look like that I have to do this? So it turns out I said there's this formula, and there's this affine constraint, but this is all convex, okay? So, okay, so I can solve this with any convex objective and any convex constraints, okay? Which is like, this is, like I could have done this in 1980, so I was like, but of course, I'm glad my students, and I almost didn't believe it. I told them exactly to do this, and then they show it to me, and I go, no, that can't be right. And then they go, this is what you said. And I go, no. And then they go, that worked that easy? Okay, so I was really, so you want to design K. So just how much does this cost? This would be what to do. This is how much it costs to compute that, depending on this. This is what this costs. Order 1 in the size of the system. Doesn't grow. Okay, anyway, that's not that important, but anyway, let me show you what I'm going to kind of jump ahead here.
Sorry, can you,
This is the formula.
John, I think
Yeah.
I lost a little bit, sorry,
Okay.
can you explain what K is?
Oh, the K is a controller. The controller is what's in this box.
How is it different from you?
U is K produces U. Sorry about that.
No.
This is all,
I understand.
okay,
Yeah.
I'm skipping over.
No, it's fine, yeah.
Good, thanks. So in this dotted box is K,
Got it, now,
okay? In K. But K has this internal structure. And notice the internal structure has the same sparsity as M and R. And so I think this is what's implemented in the brain. I want to show you why. Because this can have delays, everything in it. Because we put the delays in M and R, and then they reflect themselves in the inside thing. So notice this internal model is the internal model of the closed loop system, not the open loop. So once you do this, this is given. Okay. So but let me just say what's going on here. So let's just say what happens. You get a measurement. You compare it with what you told the controller to do. You get a new error. You send that error to the controller, it says, get rid of this. But it says, I gotta still keep track of the consequences of that. So this is internal feedback. And it's predicting your own action. Okay, this is active, whatever you want to call it, active inference. Okay. And what this lets you do is it lets you put biologically realistic constraints on M and R, and then they become constraints on K. Okay. This is kind of a miracle. What we want to do is, okay, so let's compare this with this. Okay, so I had to flip this upside down because I want to compare it with that. So this is the sort of standard predictive coding stuff. And the model in here, the Kalman filter model, is the open loop model of the plant. Okay. This is a closed loop model of the whole thing. So inside your head, you have not a model of the world, you have a model of you and the world interacting simultaneously. Okay, and you have to do that because inside your brain is slow hardware. You have to build it this way. You can't build it this way because these things are delayed. If those things are delayed, this doesn't work. Okay.
Then do you have a transfer function from the environment to the internal states of the system? It's kind of like where I'm confused. You only have one X that crosses the dashed line, right?
Yeah, let's go.
So if you have an environmental external disturbance, like how does that transfer into the?
That's a disturbance. That's in the environment. It hits the plant. So, and then that's reflected in the X. Okay. Does that make sense?
So that's the input to the plant. That's.
This is the disturbance to the plan, and this is your control action, and they add up. But the disturbance can go anywhere in this model, okay? Doesn't have to, but could. Does that make sense? There's two things. The state propagates, can be spreading all over the place if you don't do anything. This kicks it, and this tries to control it, okay? And then what it says is you sense this, you produce this error, and this is a prediction error, but it's a prediction error of the consequences of your action, right? Okay. And then this says, okay, well, that's error. What's the best thing I can do to kill that? Okay. And then I just keep going. So what I want to show is, well, how would this actually be implemented?
So can I use that?
Yeah.
How is R related to A?
A's in there somewhere. Well, we're not designing A, we're designing R. R is R, all we care about R is now is R. A is gone.
But what does R do here? What does it compute? What it? Z-
It computes the unexplained error. It tells you what the delta was that hit your plant. Okay, let me just go back here. You don't know what this is. All you know is this, okay? But you know what you did to the system. So anything that deviates from that has to be that. And then you say, kill that last one. So each time step, you're going, what just hit me? What just hit me? What just hit me? And then what I know is, I know what part of what just hit me is due to me, my own motion. So I'm moving, I know it's due to my own motion. If something hits me, then I know that that's caused by external disturbances, and I got to push back.
R computes the unexplained.
This computes the unexplained part of X. The part of X that isn't due to me is due to that. And then I have to take action to get rid of that.
So delta hat is an estimate for delta.
Delta hat is my best guess what delta is.
But you don't know R because you don't know delta.
I designed it.
But you
Yeah.
So what happens when you've got two forces acting at the same time? So normally what we do, so the pilot, and the plane example.
They do happen at the same time. They do happen at the same time.
Is it the external?
And this sorts it out.
The pilot grabs a stick at the same time, the wind blows the right direction.
Yep, both of those happen at the same time.
You can design R because you know what A, B, and you know what A and B are, right?
Offline.
Yes. Offline.
Offline,
You know
yeah.
what A and B are. You know the
Yeah.
dynamics of your system.
Yeah. Now, if you're going to do this all online, what you're going to do is just directly estimate M and R from data. But if you have an offline model, this is what you do. I'm not going to talk about data. I'm going to talk about, you have an offline model. And then you build these things. And then but these don't have A and B anymore. They just, you had A and B in the design process. Now, if you got to learn these things, you don't learn A and B. That's the old style thing. You'd actually directly learn M and R. But that works way better. That was one of the blockbusters in Carmen's thesis.
But so it's really important to know that the internal communication is faster than the perturbation on your body is in the physics. So
If you want the things that kill absolutely perfectly, yeah. Otherwise, no. We will allow some leak.
where do I see this here? That you get a problem if that's not the case.
Then your convex optimization problem is infeasible.
Yeah.
Okay. If we have time, we can go through all of that too, but so you don't have to actually kill everything. You can let it leak.
No, but these that the pole in the plant filter, right?
Sorry, this Z is just the delay, the Z transform discrete time.
Oh,
Sorry.
Oh,
Okay.
One time step like that, right? Okay.
So what I want to do is I want to say what the microcircuit would be for this. Okay. So this is what this thing is. Okay. But what I want to do is say, what do we do at each position? So every place you're creating an error because you have a state, you're gonna chop all this up. So this is part of the state, this is part of the state, this is part of the state. So notice that this is at time t, this is the k plus first part, this is the k part. So I'm chopping the state into pieces, okay? And this side measures this part, this guy measures this part, this guy measures this part, okay? And then they all produce their estimates for what their part of the delta would be. So now what we have to do is locally communicate this to your neighbor. Okay, so that's local communication. So now what's happening is, what do I do next? I take my neighbor's information, I take my own information, and I now take the action that would correct for that. Okay. So what it's like, I have a couple neighbors, and what we do is we just got hit, okay? We share that information, but only with our neighbors, or with our neighbors and our neighbors' neighbors. I can control how much I share and how fast I share, okay? So what ends up happening is now my actions depend not only on what I found out about from my measurement, but from what my neighbors did. But my neighbors, that's based on them saying what they were surprised by. They tell me what they were surprised by, I take what I was surprised by, and I update, okay? And then I do this, and I create my own new local error. And then I take a local and then okay, this is, so now but you have to have local memory, because I have to keep around what my neighbors have been done up to a point, and then I throw this away and I move the memory over, okay? So now turns out what this trades off is you get cheap communications, but the price you pay is you got to have a lot of memory. So normally you only need one copy of this. In a regular control or centralized control, you need one copy of this. You need a copy of this of you and your neighbors all the way along, okay? So you have to have a lot of memory. Yeah.
But I guess these also have to be gated by some uncertainty about the communication from your neighbors.
Yeah,
Right? So I guess in the old way, you'd have this like uncertainty Kelvin game. So where would this be in this?
Well, so what we didn't have here was measurement noise.
Right, sure.
So if we have measurement noise, the picture gets more complicated, but it all still works. Yeah, that's right. Yeah.
And what if we have malicious neighbors?
Oh, yeah. Yeah, so that's probably the most important thing to put into this. And then that's robust control, and now I have to put together this with a robust control. And here's what's easy to do. If you have a malicious adversary who is omniscient, knows everything in the world, but is only limited in where they can act, it's actually easy to protect yourself with that, more or less. What's hard to do is it's hard to put constraints on the communication of your enemy in a way that you can exploit it. We don't know how to do that yet. And the big problem is, what if you don't know who's your friend and foe? That's really hard. But if you know who your foe is, you can kind of be conservative and say, okay, I've got these enemies out there, and I'm going to kind of take a worst case scenario. I'm assuming that they can communicate with each other a lot better than I can communicate with my teammates. And I'm going to protect myself against this sort of super enemy with much higher tech than I have. Okay. The next problem is to solve what if my enemy has low tech like I do? So this is a somewhat paranoid view of the world. So you have all this local stuff, and then so what is this locally? Okay, so I'm going to consider a node with an actuator. Okay, so what ends up happening is these nodes might not have actuators, but they still see states. So they got to keep doing this and sending it to my neighbors. So if I don't have an actuator and my neighbors do, I still have to take in a state, do some processing, and send it to my neighbor. And also maybe take something from my neighbor and send it over here, depending on what the span of it is. Okay, so you're doing all this local computation. Okay, so what ends up happening is you have to keep a space-time picture of the past in memory. Okay, and then what happens is every time you update it, hopefully it shows here. Okay, so what ends up happening, let me go back and say what this is. This would have been the global stuff. But now once you design these things, and that's a convex optimization problem, sparse here, dense here, but limited, okay? And that's what I want to do. And it's a convex optimization problem to check the feasibility of this. If that's feasible, I know there's a controller K that I can get, and I can build it out of this so K has the same sparsity as I imposed on the closed. So that's why closed loop sparsity translates into controller sparsity in this direct way. That was a miracle. Like, why I didn't think of that before, but I didn't. So the reason I think this is interesting is because this says this is sort of what I told you, these microcircuits are sort of universal circuits in the sense that they need to have this feedback. And what is the feedback doing? The feedback doing is, in the simplest case, predicting the consequences of my own action that isn't explained by that. So it's the surprise I have that I attribute to something in the world, okay? And in this case, I attribute it to just being random noise. What you want to generalize this to, which we have, which is you want to attribute that to either, but here's what you do, is you attribute a lot of it to friends. So this has solved the problem of how do you cooperate with friends through limited communication. It solved that problem. And so we think that this is, so our expectation is this is how the brain works. So what happens is internal to your brain, everybody's friend. So if you don't have cancer, everybody's a friend, okay? And so what you're doing is you're doing this inside your brain, we think, with a fair amount, needing a fair amount of memory, but with limited communication. And now the question you might ask is, what happened if you're actually slower than the plant you're doing? Well, then you can't get these clean pictures. You can't get this. It will leak, but you can still do it. You just can't get this crisp. You don't care about this. You really want to, you just want to stop this, okay? And you want to do it locally and sparsely, okay? So now for the first time, we have the crank to do this. So if you're thinking about, do we need internal models in a world where we don't have all those speed of light, red, blue, or those blue arrows I had in my Kalman filter? So we can't build a Kalman filter because we don't have speed of light, okay? What do we build instead? We build this thing. And what it can do is it can't do this, but what it can do is, and the point is, typically, if you have reasonable delays and all that kind of stuff, the actual cost of this is very little less than this. So we looked at sort of reasonable things about the power grid. We tried to think of sort of reasonable things about a various bunch of things, but that all needs to be worked out. So the point is, you can do, the performance is just about as good, but you can do it with much cheaper. This is infinitely expensive, and this is much cheaper actuation and much cheaper communications, and you still get essentially the same level of performance, but it's contained and localized. Yeah.
So you said when the plant is faster, it leaks out. Does that mean you actually suppress the error to zero at some time or no?
Well, it will exponentially decay. So it doesn't go perfectly to zero. So when I drew this was not right? This is actually exponentially decaying, right? But at some point, exponential decay at some point is so small, it's not a big deal. But what happens is, if my physics is faster than I am, what I do is I knock it down, knock it down, but then I stop acting and it leaks. But other people are taking care of it, so it eventually goes away. But I can't get this crisp cutoff. So I don't have to be faster than the plant. But if I'm way slower, just take it, suppose I'm so slow that I get hit and I sit here and I sit here and I sit here, then it's just run an open loop, right? So now there's a trade-off space. How much do you want to stop it and versus the communication speed? So now you have a design tool. You can come in and say, okay, comms guys, how much is it going to cost? The actuator guys, how dense do we put the actuators? How dense do we put the sensors? And all of that can now be done in a convex optimization problem. All of you are going to guess right away. We're going to do a lasso regression. We're going to do all the usual stuff you do in convex optimization to be able to, where do we put the sensors? Where do we put the actuators? But the nice thing is it's all convex, it's all closed loop. And we can systematically trade off the cost of communication, the cost of actuation, the cost of sensing. All that gets traded off. How dense do you make the communication? How fast do you make it? All that becomes possible in trade-off space. And 10 years ago, that was the heart. If you wanted to ask control theorists, what's a complete nightmare that you ought to be able to solve? They would tell you that. That would have told you. Okay. And we have nonlinear extensions. So pretty much all of control theory that existed pre-SLS, we can port over to post-SLS. So for example, the most important nonlinearity to deal with is saturation. You get saturation. Can you do MPC like this? Yeah, you can do MPC like this. So all the things that we used to do, we can now do with this machinery, okay? And so for me, this is the biggest thing that's happened in 50 years, relative to what we can do, say, for the power grid or for the internet. And
How
so,
do you learn R and M from data?
yes. And the other thing, this is what's cool
How
about
do
it.
you? How do you?
I'll tell you, okay. Well, ask Carmen when you get back. But here's what you want to do. So here's the problem, the traditional problem with system identification. Is you never see open loop data unless you have a wind tunnel, right? If you just have a real system out there and it's not working very well and you're getting some data and you want to refine it, you don't get to take it offline, right? I mean, sometimes you do, but in this case you don't. So the point is, all your data is taken closed loop. So the best thing you can do is to estimate what these should be, okay?
Yeah, it's actually easier to estimate.
It's
right?
easier to do these. So you just do everything closed loop. And there's this Willems lemma stuff that you can actually dispense with models of this altogether and just use data everywhere. So you end up with a system where you're doing MPC, you're doing everything, and all you have is these summations of all the data you take. Now, that's Carmen's thesis, and she got the Collins Prize for it. So it's a significant bit of work to have done that. But the point is, what you don't want to do is try to figure out what the A and B are.
Yeah.
Because they're all, I mean, there's some god awful, the dependence of this on A and B are so back in the optimization stuff, it's a mess. And so you actually want to work entirely in these closed loop M's and R's. And so that completely changes how you do any kind of learning in the context of this robust control. So, and you got the world expert, at least in Zurich, for another month. So you want to learn a little more about it. And then she's going to be at Stanford. So, and I'm doing a really lousy imitation of her. But she's also like, she doesn't speak so loud and stuff like this.
Somebody trying to come in because the door locks itself. Anyways, it's past 6 now.
So I'm sorry, that's kind of a, but it turns out the stuff I didn't tell you isn't that hard. Once you understand what the parameterizations are and how to put this stuff together, that's actually the hard part. So I showed you all the hard part with cartoons. It's not that hard. You're all running convex optimization problems. And then you can put all sorts of bells and whistles on, right? You can do all sorts of regularizations. So it really sets up this thing where we can, when we get to this, we've decided what the lower layer has to do. We can put constraint after constraint after constraint after constraint. It stays convex. And you produce these localized controllers to do localized control. So that, like I said, that's, to me, it's still kind of a miracle.
So, no, you did say that
Yeah.
there's a circuit in the brain that does this.
We believe, okay. If the brain is implementing this kind of control well, it has to do it this way. I mean, it could be this shit, right? Okay, so here's a counterexample. Here's an example where the brain doesn't do it this way. This nerve that goes all the way down the aorta and back up here. That is clearly suboptimal. The laryngeal nerve. You guys know about,
Recurrent.
What?
It's even called the recurrent.
Yeah. Okay. So why do we do that? Does anybody know why? Evolution. You go back and you look at what it is in a fish. It's a straight line in a fish. And then you morph a fish into us, it has to go around the and all this. And a poor giraffe goes, oh no. So I'm not saying that the brain, this is what the brain would do if it was optimal. Okay, but what we can do is we can put in the constraints that the brain has. What can spiking neurons do? Well, those constraints we can put in, and those can be constraints of evolution, good or bad, right? What we can't do is put in system level errors in evolution, right? Where you get a mistake. You can't, we're not gonna be able to predict that, but you could actually put that into the model, I think. So if you knew that there was that limit in the communication, what you'd say is, okay, this wiring is slower than the wiring should have been. And then you put it in, and you can just add it to the constraints on what this is. And then you can design the optical controller given that constraint of the nerves. So you can, I think, go through and put in a lot of the sort of issues that would come up as a consequence of suboptimality. So the point is, the other thing that's really good about this way of doing things is, if you design an optimal controller and your subjects don't behave that way, it's because they have a constraint that you didn't put in the theory. So it's very productive experimentally, because now you go out and say, okay, what was I missing and what do I need to add? So it's so if I just come up with some model and the model doesn't fit the data, what do I do next, right? But here it says, I can focus on what in my model did I capture? And also their behavior will often tell you right? So you do this experiment, you decide how good a driver is, and you go and do the experiment, it completely fails, and you go, what went wrong? Well, the driver was texting, and you didn't have that in your model, right? So what you probably do is tell them to stop texting, but if you wanted, you just put, oh, you got a multiplex texting along with driving, and now all of a sudden the performance is gonna degrade, and you're gonna predict the performance is gonna degrade. But you have this iterative loop that isn't there if you're just doing modeling, design and modeling stuff. It says, I'm telling you what the optimal thing is, subject to these constraints. So either I'm right or I have the wrong constraints. In either case, we have a round of experiments and theory to do, okay? So, yeah.
Can I follow up with that?
Yeah.
So like, brains are kind of characterized by neural reuse, brains reuse the hardware, you can't just
Yeah.
add new compute, and so you need to be able to flexibly like reassign, chunks of brain to do different types of tasks.
Yeah.
And also, synchronously, especially human brains are always optimizing multiple things at once.
Yeah.
Not just controlling one thing,
Yeah.
one task. So how does your system like deal with like that, kind of like the synchronous and asynchronous, like?
Well, I mean, if you had a centralized computer, a single centralized computer, okay, it would still have to adapt and learn, okay? All this changes about that is this now is a localized problem, so you can have just parts of the brain adapt and learn. You don't have to have the whole thing learn. But otherwise, the only thing that changes is that now you're going to learn in closed loop, not open loop, which is a much richer and much more effective way to do this. But all it does is it distributes the problem that you just described to, so you have brain regions that would switch from doing one thing to another. But it doesn't change the need for you to have a framework to do that switch. So it doesn't change that about the subject. It just lets you do that now locally.
This is a framework to do the switch, just a higher level of control.
Yeah, that's correct, right. So it wouldn't change the need for that. So you still need layers, and this is just the algorithm within one layer, right? Yeah.
I was gonna ask exactly that question. So if I look at your picture on the right geometrically,
Yeah.
the R is continuous in state space and it's continuous in time. If I look at the M, it's sparse in state, continuous in time.
Exactly.
So what we need is to get something that's sparse in time. So would that be a collection of R's with different, if you will, time constants?
Yeah, so you can,
Because I want to draw your two lines like that, but in the time direction.
yeah, you can do that too.
Yeah,
So that's,
that would be, yeah,
so that would be a situation where we're not only in space can I only act at certain points, but I can only act every once in a while in time.
right.
That's still a convex optimization problem. No problem. I can do that. That's no problem. And so you can certainly imagine having a multi-rate system, right? Where I can act really quickly, but my neighbor only acts every once in a while. And then you're going to want to do that across layers. So that's the part I would say is a weakness of this, because if you have two layers doing this, right? So you have two layers running NPC. The lower one is running NPC in very small things, and the higher one is on slower timescales running a longer NPC. So we have a paper on this, but we're not solving the. So here's what you'd like to do: you'd like to put the whole problem together, push a button, and it tells you how to separate it, and then designs the algorithms.
Right.
We don't do that. We do the separation, and but doing the whole thing, push a button, do the whole thing, because the communication cost between layers is important too, right? So my students now are trying to figure out how to do that whole thing top to bottom. Okay. But Carmen's gotten distracted by language, so she's going to fix language, and she's not. She would probably solve this by now, but she's doing cool things in language, so I don't want to. Anyway, so the problem is just like one Carmen, so that doesn't scale. But then Nick Motney's working on this. Lisa Lee, who was last summer, she's working on this. So a lot of people that are like way smarter than me, but don't speak as loudly. So they're working on it. And so I'm trying to figure out. I'm trying to use the ideas from this to try to understand the immune system and what goes wrong in cancer and what we can do to, how do we intervene to speed certain things up or turn certain things off in order to, in this case, stop metastatic breast cancer. So it's looking really good. So some of the stuff that came out of this is suggesting new therapies that so far work in mice. So many stuff works in mice that don't work in humans. Yeah, but there's a whole lot of control. I mean, all of nonlinear control theory is still sitting there to need to be added to this, right? And that's what a lot of people do. And the first thing to do is fully do MPC this way. Okay, and that's what Carmen did in her thesis, but that was just, a couple of years ago, right? So it's where this is really the bleeding edge of this, right?
That was linear MPC or non-linear model predictive control, distributed non-linear MPC.
Well, the nonlinears are usually gonna be saturations,
Okay,
but those are the ones we care about. There's two kinds of saturations. I can only go so fast, and if I hit the wall hard enough, I die. So these are hard limits, right? And those are the things that matter, and those are the things that MPC is best at. And so you can put all that in
well,
there.
also the nonlinear dynamics, right? There's a lot of nonlinear dynamics, even in couple is nonlinear, dynamics is nonlinear, they're fundamentally nonlinear. And any kind of chemical plant is exponential in the products of the reactants and stuff like that. That's also the nonlinearities that people care about, right? It's not all just small signal controls for stability.
Yeah, so this doesn't do anything dramatically better to fix that. All the stuff you would have done in a centralized case, you can still do here, but it doesn't magically make those nonlinearities go away. So you're still gonna use control barrier functions, you're gonna still use all the machinery you did before.
Okay.
And it doesn't magically make that go away, right? So one of the things you would do in this context a little bit is do more of the set chasing, because you're working with such much smaller state spaces. The one thing it doesn't aid is you're working with this greatly reduced localized state space. So as a consequence, you can do algorithms you would never run before. So you can start doing MPC-like things because your state space is so much smaller. You can do this MPC on much richer models than you could have had to do it for the whole thing. So there is one advantage to using this if you're just cared about nonlinearity, is all the tricks that we have to deal with nonlinear systems are expensive. They're expensive offline to compute the controllers, and then the actual computation online of MPC for highly nonlinear is very expensive. So this thing cuts down the size of the state space because you're doing everything in patches. So it does have that benefit, but it doesn't fundamentally change what you do in a patch. Okay, it just makes it small. So I should have been clear about that. Yeah. All right. So, anyway, thanks.
So yeah, this is work that we've all done together with Lau Muller, Perry, obviously, and my advisor Max. I think all of these people love waves. So I'm going to go over briefly a little bit of motivation of my research in general and kind of how I approach these problems and why I'm doing things the way I'm doing them. So I think it's a little bit different than a lot of other computational neuroscience research. And this motivation, I think is kind of best stated by, there's this interview with John Hopfield and Lex Friedman of all people. In 2022 or something, he asked him, what does he think the main differences are between kind of biological and modern artificial intelligence? And he said, this is a direct quote. I think he phrases things really well, so I'll just read it verbatim. One thing that very much intrigues me is the fact that neurons have all kind of components or properties, and in evolutionary biology, if you have some little quirk in how a molecule works or how a cell works, evolution will sharpen it up and make it into a useful feature rather than a glitch. And that aspect has been completely suppressed in artificial neural networks. And so after this, he started talking about oscillation and other types of things that are in biological systems that are missing in artificial neural networks. And he thinks from this kind of reasoning, there's probably some useful purpose to them. So I'm wondering, what are those useful purposes? And to kind of emphasize that, he told another story that he used to drive this old 1945 car, I don't remember the make of it. And he said anytime he would go over 45 miles an hour, the wheels would start to shake, right? And so basically, that was a really effective speedometer, right? He didn't even need to look at the speedometer. And so if this was a neural system and it needed to know when it was going above a certain speed, it wouldn't have to worry about where that signal came from. It would just kind of capture that signal.
This explains oscillations.
Huh? Exactly, something like that. So it's capturing this like natural signal and then learning to use that for some beneficial purpose. And it doesn't have to worry about why it's happening. So I think one of the questions that I think about is like, how do we find the uses for these natural phenomena that we see a lot of? And I'm going to argue today, maybe slightly provocative, you don't have to agree with me, that maybe we can build really scalable machine learning models that integrate these mechanisms, and that can be a way to find out their functional purpose in a way that's different than you would find with really small models that don't scale as well. And so why do I think that? I think Terry at the very beginning of this session talked about revolution in neuroscience. That was, we have the ability to record from tons and tons of neurons, way more neurons than we could ever record from before. And I think there's another revolution which is happening on the machine learning side, which is these scaling laws. This is a paper from the OpenAI folks, now it's ancient 2020, where they showed that the loss of these large models, as long as they're not kind of bottlenecked by one of these other properties, that the loss decays with some power law as a function of kind of either compute or the data set size or the number of parameters. And now if you look at all these large language model papers, everyone does a plot kind of like this, where they say like, okay, I just keep scaling the number of parameters and I show my loss decays with some next function. And basically this just seems to continue to happen. And I'm going to argue the reason that this works, what allows this, is we've really developed these scalable architectures for machine learning that can just add more layers and we can still train them. This isn't so easy. I think many of the people here probably know, like, it was very hard to do until not so long ago to just make things super deep and have them still be trainable. And I think one of the first examples of that was this AlexNet architecture. The reason why this succeeded, I think, if I've heard Jeff Hinton give this answer, is that Alex Kruszewski basically was able to put this onto 2 GPUs at a time when nobody else was able to put these type of convolutional neural network. Nobody had any idea how to do this, and he wrote the CUDA kernels, did it all himself, and that allowed him to scale to ImageNet when nobody else was able to run these models of that size. So that was kind of one of the first scalable deep neural network architectures in my opinion. Yeah, then I think one that everyone's probably familiar with is the transformer. Attention's all you need. Basically, you have these blocks and you can just increase the number of these blocks to as many as you want in the thousands, and these things still train. And the reasons for this, like Terry pointed out, are you have these residual connections, you have these normalizations everywhere. People have really tuned this thing up to make it so that it does scale very, very well with the number of parameters. And then finally, what Terry also mentioned are these state space models. So these are much newer. And the reason that these scale so well, which I'll go into a little bit later at the end, you have this kind of linear recurrence relation. And what they showed, or kind of what made them able to run this at the same scale as transformers, is that you can turn this linear recurrence into a convolution over the entire sequence length at once. So this convolution kernel is the size of your entire sequence. So you can effectively process, instead of doing it RNN where you process every element one at a time, and I'm sure everyone's had a for loop in Python that goes incredibly slow, you can process the whole thing in parallel.
But that's not really true, because when you're training RNN, you basically unroll the computer anyway, right?
Right, but so I'll describe the algorithm at the end. It's this parallel scan algorithm.
Okay, yeah. Well, did you hear there was a tutorial about it earlier?
I missed it, so yeah, that he'll probably have explained it much better than I will. So I might skip that part.
From Jason, he mentioned parts of it.
Okay. But basically, this is another kind of highly scalable method that is now like in the recurrent neural network setting. So if we can put kind of these natural computational mechanisms into some of these architectures, I think that's really cool as a way to test what these mechanisms are useful for, right? And I say maybe this is a little bit related to the bitter lesson from Rich Sutton, if anyone's familiar with that, but basically is like, everyone tried for a really long time to hand engineer things into these neural systems, and the bitter lesson is basically compute wins in the end. If you have something that can ingest more data and scale better, that's going to take over in the end. So you don't have to agree with it. What I'm saying is maybe for computational neuroscience, it's interesting to see how we can embrace that. And so as an example of that, I did some work in my PhD, which was we look at kind of topographic organization of functional selectivity in like area IT of the visual cortex. So here are fusiform face area, parahippocampal place area, two regions of cortex that are specifically selective or responsive to images of faces or places. And people have various theories for how these regions form, why they're localized like this, why you get these little chunks. And basically in my work, what we said was we put some topographic constraints, so a correlation constraint into a convolutional neural network, into the final layers that allowed us to train the model on a big image data set. And then when we look at the selectivity of the neurons in that final layer, we see that they cluster according to faces, bodies, places, and stuff like that. So what this told us is like this functional selectivity may just be a kind of, I don't want to say emergent, there's probably a better word for it, some property of having a correlation penalty in your latent space and then training on a ton of data.
Like a wiring penalty.
Kind of exactly like wiring. And so people in Jim DeCarlo's lab had a second paper after this where they showed a wiring like penalty does the same thing. But in a convolutional neural network model, basically these were the kind of the first papers showing that these things could be learned rather than like built in. Like if you just have a wiring link penalty and then you train the whole thing, that stuff is learned. Anyway.
Isn't the key question really what else could happen? So if you do it from a statistical mechanics perspective, you get all these domains forming, and the nature of the constraints in this statistical mechanics formulation would tell you how big the domains are, et cetera. There are very rich theories about where the boundaries are between domains. So the really interesting question here is not that you can get these domains to form, it's what are the details of that and what else could happen?
Yeah, I think one of the cool things, I don't have this, maybe I have the slides somewhere else. Oh, by the way, this was work done by this fantastic master's student, Ching-Hee Gao, who's now doing his PhD in Eindhoven. Yeah, one of the cool things that we found is that like you see the body and the face clusters are a little bit overlapping. And this is actually what you see in the cortex as well. These clusters are right next to each other, and probably because you often see bodies and faces together at the same time. And we, yeah.
Sorry, but how robust is this? If you train like 100 VAEs, you get the same map every time?
It has a little bit of a permutation to it, but you get something roughly similar. Let me see. I have slides where we show a bunch of different, I have to find the slides. A bunch of different random initializations. You can see I stole
How many
slides.
slides are even see going?
I can show you those later, but it's fairly here. This is it. So we train it a bunch of different times. We even try training it on different data sets, and you still see the shapes change, but always the face and the body cluster are close to each other and overlapping a little bit. We also not super convinced, but it's like I think definitely more work could be done. This was a very quick project and pointing in that direction. Okay, I don't want to spend too much time on that because that's not the point of this whole talk. I also had a second part that I'm not going to talk about. I'm just going to talk about waves. So waves in the brain and how they may be used for memory or computation. Here you can see like maybe these are areas that spike, waves are propagating out, causing some disturbance over here. Okay, so very early measurements of waves. There are even earlier measurements, I think going back to like 1934 or something like this. This was from 1953. And the reason that I put this in is because they have a plot where you see the wave right here. So this is measurements from 7 different electrodes of kind of a spike, a stimulus, and then you see the time down here, and you can see the peak of this excitation moving to the right as you go further in these kind of in the distance on the cortex. So this stuff has been seen for a very, very long time. This was the video that Terry was trying to show earlier. This is in the hippocampus. You can see these waves propagating across.
Yes, roughly 5 hertz. So it's slow down.
Oh, okay. I see, yeah, and so here, this is at a velocity of like 1 millimeter per second. These were these waves traveling that Terry did show from the EEG, I think it said from babies. This is 2 to 5 meters per second, so a wide variety of scales and velocities across regions of the cortex. These waves are definitely there. Let's see if I have more. I do have more. This was work from Lyle's group. This is in V1. This is stimulus evoked, I think, through voltage sensitive dyes, or and you can see this propagation. And what they see is in V1 and V2, there is a simultaneous propagation of waves that kind of mirror each other. This is in area MT of a marmoset. You kind of see a wave moving in this direction. Anyway, so I think the reason I put these in is there was a quote someone said earlier today. We are neuromorphic engineers. What can we use this stuff for? I don't remember who it was. And so I would say let's scale it up and see if we can find out. I shouldn't have put Lyle Max here. I don't know if they agree with scaling it up, but this is what we started back almost a year ago for this project specifically. And so I think when you go to test some of these ideas, you need to have, it's helpful to have a hypothesis of like, what do I think this thing is going to do? And so that I rely on the intuition of people who are much smarter than me. And this was from, I think, Terry and Lyle's review paper. They mentioned this specific paper where this is from a physics journal. They called it the wave-based Turing machine. But the important part of it was that if you bounce a droplet, I think it's a
Slaveryism. It's a plastic and it's on the oil
on an oil bath.
bath.
Okay, so it's able to bounce and they're oscillating the oil bath, something like this. The droplet will move along according to some random trajectory just that's governed by kind of the phase of the wave field where it lands. But the interesting thing is they can do a slight shift at some point, so provide a little jolt to the wave field, which causes the ball to shift by like half a period in whatever the ongoing oscillation is. And what happens then is the ball actually bounces on the waves in the opposite direction of the way that it was going. And they show that it exactly traces the reverse trajectory that it had just followed in the forward direction. So their argument for this is that this is showing that these waves are storing the entire history of where that ball has been in the past. Basically, the ball has moved to here, you provide an impulse, and then the ball can move and perfectly trace that path backwards. The idea is, okay, the wave field is somehow storing the history of the previous impacts that are happening to it. So maybe we can use this as a memory store in a recurrent neural network. And so
It's not a consequence of the fact that it's periodic, and so if you know where it is now, you know where it's going to be in the future, you can go backwards. Is that just the city coming through in various forms?
I'm not sure. I would think it's some reversibility of the dynamics.
Which is possible with the oscillation.
Right, yeah.
They did some math analysis of it. They showed that, it works out.
And they think they argued even in like a chaotic regime, it was still able to.
This is standing.
No, these are traveling waves.
I think
These are snapshots of travel. You can see the interference patterns.
So yeah, one of our ideas is like, okay, how is this going to be different than like what a regular RNN is doing and when it tries to store things in memory?
There's something called more reciprocity in waves, which basically, if you sort of flip the argument, you get exactly the same.
I think that's exactly what that was. Yeah. Okay, Helmholtz reciprocity. Good words. So our argument was like, okay, so you have input coming on 3 channels. Terry already kind of showed this example with the 1, 2, 3 example. Maybe our wave RNN encodes this. You see like the first thing, it has an input on channel 2. There's a bump here. The second time point, that bump has moved a little bit. There's another input, an input on channel 1. The third time point, there's no inputs on these 2 channels, so there's an input here. You see the waves are kind of propagating at each time step. Whereas if you don't have a propagation and you have what we call a static bump system, you're effectively going to lose the information of when 2 bumps happen on a channel sequentially, right? So channel 2 here, we see there was a bump at time 0, a bump at time 1, and then no bumps for the rest of the time. Whereas in channel 1, there's no bump, no bump, whatever. Channel 2, it's impossible to decode from this final state what the sequence of these bumps were. Whereas here you can clearly see, obviously we're using more neurons here to encode this traveling wave, but we can decode the full history. Just a schematic again. Okay, so now how do we build a scalable RNN that has these waves in it? And this is where I'm going to go into the model and what's in that notebook. So this was this paper from Zach Davis and I think Will Muller's group as well, where they built a large scale spiking neural network that I think Terry mentioned. And what they showed in this paper is that if you have a spiking neural network that has local connectivity, so connectivity that has a kind of probability of connection that decays exponentially with distance, like a Gaussian, and you have some time delays that are a function of distance, then in a certain regime of an inhibitory and excitatory strengths, you get waves. They have some metric for how wave-like your dynamics are. And these are the equations that describe these spiking networks. And you can see this is their example, and they did a bunch of analysis and showed that these waves match cortical waves according to a bunch of statistics. The challenge with this is I don't want to like upset people and say scaling or spiking neural networks are not scalable. I don't know very much about spiking neural networks, but what I will say is I personally, and I think as a community, we know how to scale like an RNN or like the state space models better to real world data sets than we do know how to scale spiking neural networks right now. So how do we take these principles and put this into a recurrent neural network?
This is a question. I mean, isn't this like this is excitable media, right? This is the example from like Turing patterns emerging or whatever, right? Or is there anything different here? Because like the local interaction and then a refractoriness or something like this gives rise to waves.
Right.
Right?
Yeah, I think there's a lot of ways to understand this from a lot of different kind of higher level abstractions. I think the exciting part about this is that, I mean, this is like fairly biophysically detailed in comparison with an RNN, and the statistics of the dynamics end up matching very closely what you see with real waves in the brain, which is not the case for like reaction to fusion patterns.
So that's a conductance model. And
right.
you can see that the G's stand for conductance. That's basically the flow of ions through a channel, and E is the reversal potential, and V is the voltage. So it's being driven by that difference. But you know, so it's more than just a weight. Conductance has a different electrical property in real neuron.
Yeah, I mean, so I was inspired by this and this idea of, okay, just local connectivity, because I played with local connectivity a bit. And so that brought me to how can we get a regular RNN to have waves? My goal was like, let's put waves into a simple RNN and then compare them and see which one does better on a memory test. So that's what I'm going to show you. This is a simple RNN. Your hidden state is some vector of neurons, so real numbers. You have some nonlinearity here. We call it a rectified linear unit. You have some fully connected hidden to hidden coupling matrix here, some matrix that reads in your input to the hidden state, and some bias. And so if you look at how this hidden state evolves over time, this is a video, you can't really tell, but it's like that bump system I was talking about before. The neurons are getting input, but they're kind of, the input's not spreading anywhere because there's no notion of local connectivity. The input can move kind of randomly, whatever is defined by this U matrix. You're not going to get anything like spatio-temporally coherent. This
How do you plot this vector of hidden states as a 2D picture?
I just rasterized it. Yeah.
Then why do you get those bumps then? Is it periodic? if you're plotting it just by as a raster.
Each one of these is a pixel and it's just blurry because.
Oh, I see, okay.
Sorry. It's not a great example, I need to
Hold on,
read it.
just so we can get the model, so the number of neurons is D,
Is N here.
N, so what's D?
D is the input dimensionality. So we have some input sequence that is vector.
Oh, so X is the input.
Right.
I see. And so the state space is this n-dimensional vector of neural activities.
Yes.
Of which
Well,
is
and the hidden units also, right?
HT is the.
HT is the, yeah, this is the
That's right.
state space.
Yeah.
And what are you doing?
And I'll go over the exact data set, but it's D is actually 1 and it's a sequence of pixels, and then at the end you have to classify what image it was.
But so is this a random initialization or?
I think this initialization is actually an identity initialization for you. This was a model that was developed by Jeff Hinton. They called it the identity RNN, and they said it works better for long sequences. Random initializations work pretty poorly on these tasks. So Terry already gave away the story earlier today, but the secret to how we can get waves is replace this dense connectivity matrix with a Toeplitz matrix, which in kind of the deep learning world, we will often implement as a convolution operation. So you have some kernel involved with your hidden state. It's actually a cross correlation, but we call it convolution. We can argue about it, but I don't think it will help. So what we do in that case in convolutional neural networks is you typically have a number of channels. And if anyone's familiar with image convolutional neural networks, your images have like 3 input channels RGB. Then as it propagates upwards, you have more and more channels. Each one of those channels is determined by a filter that goes over the image. So what we're doing is we're doing the exact same thing here. We break our hidden state into some number of channels, right? And we're just kind of splitting it up.
So people talk about normal RNN as having decaying weight activation function, weight, effect over time. But do you need this to be unitary so that you actually have energy preserved network over time?
That is how people have been doing this, yeah, in the past. So I think that's like this identity initialization, and people have done these unitary RNNs and orthogonal RNNs. And I think that does help, but it's not the entirety of the story, if that makes sense. So
Toeplitz is a magic thing.
it seems to be pretty magic, and I'll give some more evidence besides just that other people are using this as well, and it seems to be very useful. So this is what the hidden states look like. This was that video I showed you before in the wave RNN as it's processing the sequences. At the beginning of the sequence, there's not a lot of input. The activity kind of builds and travels. It's traveling this way, over and then up. This is a one-dimensional thing, but I'm just plotting it like this is one channel of these C channels. You can kind of ignore the channel for now. I'll explain it later. And if we plot, this is a static version of this, where this is like the plots that John was showing, where you have your space dimension over here and your time over here. And so lines that go this way are waves that travel through space over time with a velocity given by the slope. Okay, so why is it convolution? Why is it this Toeplitz matrix construction that yields waves? So we can derive it from really simple finite difference equations. I think I'm probably going pretty slow here, so yeah. I'll speed up. This is a one-way, one-dimensional wave equation. Some people also call it the transport equation. So you're saying your hidden state, the change in your hidden state over time is equal to some velocity times your spatial derivative, right? So if these are your neurons and you say they have some spatial organization, so one-dimensional, and there's some activation across them, we can label them. So the exponent is the space, the subscript is time. We extend over time. Basically, this equation, if we discretize it, says that my hidden state at a position at the next time step is equal to my hidden state at the previous time step, shifted by 1. This is if we set velocity equal to 1, right? So what does that look like in here? well, at the next time step, we shift by 1 and so forth. And this is those diagonal patterns we were seeing before. So this is just a finite difference approximation of this equation. And if you implement this in matrix vector notation, this is just a shift matrix. So this is a Toeplitz matrix. The upper diagonal here is all 1s, and then it's has a boundary condition which is circular. So you have that 1 and 4. This is also equivalent to doing a convolution or a cross correlation with this little kernel U. So these two things are equivalent. So basically what we're saying is to put this transport equation into an RNN, you can just multiply by the shift matrix or do this really simple convolution. And this is, if anyone doesn't believe me, the actual derivation with arbitrary velocities. I'll go over how you can do like, this works for any differential equation. That's kind of the cool part, which I'll go into later. You can do like diffusion equations, you can do fancy neural field theory equations, you just do a finite difference approximation, turn it into an RNN. Sometimes you need to do a little bit fancier numerical integration methods to get it to be stable. But you can turn whatever PDE, ODE you want into an RNN and get interesting results. So yeah, I will just skip ahead a little bit. Like I said, this has multiple channels. So the hidden state is broken up into these different channels, and each channel has a different filter that's acting on it. It also can be fed, it can be driven differently by the input Vx here. And so what's going to happen is at each time step, the way that things propagate in one channel is a function of all of the channels. You can actually do computation at each time step while having this kind of wave dynamic problem. The coolest part about this, the thing that excited me the most, is that even though the derivation says you want your convolutional kernel to look something like this to get waves, if I just initialize my convolutional kernel arbitrarily, so this is a random Toeplitz matrix that I'm starting with, and then I train it on this sequential task where the task requires the model to store things in memory for a really long time, it learns something that effectively is this wave kernel. So it really seems to be kind of like a normative explanation that these waves really are beneficial in this model, at least when we have these convolutional constraints in there to solve this task. So this is the copy task that Terry showed before. I won't kill it to death here, but the basic idea is you have some input sequence. So this is time over here, binary, like 9 or 10 dimensional vectors, and then you have like 10 elements. There's a time delay of t time steps, a go signal, and you have to reproduce that. And basically what we see, like we saw before, this wave RNN does significantly better on all of these lengths. And if we look at the actual reconstructions, even up to 480 time steps, the wave RNN is exactly correct. So if we compare this to this down here, those are exactly the same. The regular RNN can't even do time step 0 if it has a small number of hidden units. If we increase the number of hidden units to 625 from 100, it can do 0, it can almost do 10, and then it just washes out, or you can do up to 500. We did a bunch of other tasks. So there's this adding task. This is a task that was introduced by Jürgen Schmidhuber in this long short-term memory network paper in '97. Basically, the idea is you have a 2-dimensional vector. Your goal is you want to add together the floating point numbers in this first dimension that correspond to the location where the ones are in this second dimension. And so what this requires is the network somehow has to be able to gate the input based on the second dimension and then keep this item in memory until it sees another one. So it is, as a function of sequence length, this is testing the memory ability of the model, but also kind of like an integration of information scheme. And what we see again is that this wave RNN learns almost instantaneously on all of these tasks, can solve them up to length 1,000, whereas this identity RNN architecture does not.
But you've got some gating readout.
What just the delay?
So there is coding in here actually.
How do you decode that?
How do we decode it?
I just learned the task, so it just train to do just this one task.
It's just trying to do this one task. Yeah, there is a readout layer that happens at the end to produce the target value. It's trained through regression.
Question for this class, the readout has access to all of the neurons, right? So
Yeah.
in this example here, you're basically storing the entire input sequence in memory, right? And the readout has access to all of this, so it is multiplying the second row by the first row and summing everything up, right?
Right. That
It's, I mean, I'm not surprised that it can solve this task.
No, you're not storing the whole sequence in memory. It only stores the things that it needs to store, that's the point. It doesn't store the whole sequence, right? It only has the neurons. It doesn't have the input sequence.
Yeah, but I mean, the neurons in the wave are set up to basically form a delay line, sort of, right? They are feeding into, like, if you look at the whole network
That's true.
activity, it would look exactly like the input sequence, right?
exactly. Yeah. So and I think that's like the reason why this is so almost trivial when you think about it. It's like you're storing a short-term memory by kind of just pushing things into a delay line, right? But it
Delay
gets
buffer, right? So,
so, yeah, it gets complicated to decode once you have interference of these things, and you need to be able to learn how to control that. But it does work, and on these simple tasks, I agree, it is almost like trivial. Where it gets more interesting is on these tasks. This is where the videos I was showing before, sequential MNIST. So you show a single pixel at a time on this image, and it goes left to right, top to bottom. So this is like what the sequence looks like, these handwritten digits. And then at the end of this sequence, you take the hidden state and you have to say what digit identity was this? This was a 7, this was a 5, or whatever. So this is a 784 length sequence, and then you have to do integration of information, and you also have to classify. And this is the data set that is in the tutorial notebook that you can play with. And this is a really common like long-term memory data set for RNNs. And basically, yeah, you can see test accuracy almost immediately is incredibly high in comparison with this identity RNN architecture. You can do a permuted version of this task where you do a fixed random permutation of the inputs before processing it. And you see this doesn't affect our model at all, which kind of intuitively makes sense. Like you're saying, if you're pushing this onto a delay line and then you're processing it with something that's permutation invariant, like a multi-layer perceptron, this permutation is not going to affect it. Whereas a model that actually has to process everything one element at a time, like a regular RNN, is going to be affected by the fact that you no longer have these spatial dependencies that you had before. And the cool thing is, like, it's not just that it's better than this simple RNN, it's better than a lot of these models that were introduced much more recently, right? So LSTMs, GRUs, all of these fancy RNN type of models, we're using this really simple, stupid idea, and it seems to work better than this, with a similar number of parameters, or even less parameters. So there's something about this. Yeah.
Yeah, was this just to reconstruct the digits, or was it like training and then testing on unseen digits?
It's
like
on
regular and this.
This is on unseen digits, and the task is to classify. Isn't to reconstruct.
Tilde to the turbulence matrix as the encoder. Like,
Yep.
that's cool.
Yeah, so it's incredibly simple, and yeah, this is what's in that notebook.
So like, because you have 256 neurons and the picture is 700 and would be like 784 pixels.
Right. How is it doing it?
Right, like, is the projection from inputs to hidden states like interesting in that it's like compressing?
Yes, but we actually have 16 channels. So the total number of neurons is larger.
I see.
But we have significantly fewer parameters because instead of having this dense matrix, the tuplets matrix shares parameters along all of the diagonals. Right? And we have these really small kernels, so a lot of zeros, local connectivity. So I think it's using all of this, and I'll give some examples where it's not exactly just a delay line at the end, some ablation experiments. Yeah, versus number of parameters, we're better.
And so they state couplets.
It's It's forced to stay topless, yeah. So we're tying all of the weights. We don't allow it to move away from it.
Well, but you train the input and outputs though, right?
Yes, those are trained as well. So I have some examples where yeah, I do all the appellations of comparing where I don't fix it as toplets and I allow it to potentially change, and you do see that it does change, and then the performance decreases. So it really helps to constrain the model to force it to have this symmetry, this kind of spatial symmetry of tying the weights everywhere in space, which makes sense from like wave perspective. Another data set, noisy CFAR10, again, doing better than these other models. This is some of these ablation experiments. You don't need to go into the exact details, but like basically, even if I take this regular RNN and I initialize it with this Toeplitz shift matrix, but they're not tied, the loss is fairly low. It's significantly lower than it was in the original case. It was 10 to the -4, 10 to the -8, but compared with our model at 10 to the -12, it's still orders of magnitude worse. So really something about tying the weights in this spatial symmetry and the specific construction that we made is helpful. Okay, so that's, I have more of these kind of appellations and showing like, that's what this picture is. If I take that identity RNN, initialize it with the shift matrix, you can see initially it has these waves, but then at the end of, this is the beginning of training, this is at the end of training, you see the waves have kind of broken up. They move across some portion of space and then they die right here in the middle, presumably because these weights in the middle here are now no longer laterally connected and they're doing something else. Yeah, so I'll skip some of these other examples. One example I do want to talk about is the fact that this wave RNN is doing more than just kind of copying things to a tape, at least in this task. So the comparison of copying things to a tape would be, I take that full sequence of digits or of pixels. Yeah, I take this full sequence and I feed this into a fully connected neural network, a multi-layer perceptron, right? And then I train it to classify based on that. So this is like fully connected MNIST. That's what this line is here. You see it does well, but then it just kind of, it gets to about 90-something%. Whereas this wave RNN model, it is doing some processing in addition to this storage, apparently. So, and I believe this is due to the channels in the convolutional kernel, you effectively have like an MLP operating over time during the sequence. So you're doing processing in addition to storing the memory in the wave field.
Do you have any intuition as to why some of the tasks that didn't learn instantly, because the other tasks you're showing, it seems to pick up near instantly, but it was two tasks where there's a time delay between it. Like, could you visualize anything in the weights or anything else there that would indicate why some of the tasks were more difficult to learn? So many of the tasks, it seemed like it was less than an epoch and it had already learned everything.
Yeah, something about the difficulty of the task. I don't have a good answer. But you can see, if you like run the notebook, you'll see how fast it trains. And during the first epoch, it's not like immediately 100%. It just learns much quicker. So it does take some number of iterations.
The learning's just happening at the readout layer, or?
That's this example, but in the other examples, learning is happening everywhere. So in the real comparisons, learning is happening in this convolutional kernel, this read in, this bias, and also the readout. If we just train the readout layer, that's this example. You see it still gets up to something like 90% accuracy. And I believe this is kind of like the delay line type of example. You're getting the same performance because it works really well at storing things in memory, right? That's what you're saying. You're saying just propagate things forward. And whereas if you do that with a regular identity RNN or something like that, like this is that static bump example, it really can't. So yeah, the same idea of having local connectivity to generate waves works for a whole variety of models. So this is a model from Konstantin Rush and Sid Mishra at ETH. Now Konstantin's at MIT, I think he's gonna start a lab in Tübingen. This is a second order equation, which is a network of coupled harmonic oscillators. So if you ignore this, these terms here, it says the acceleration of my neuron is given by, is inversely proportional to my position, with some damping term. Then we can add in all of these coupling terms, so it's coupled to other neurons, there's some damping coupling, and it's also being driven by the input here. Basically, it's a network of coupled oscillators. If you just look at what the dynamics of this model look like, because these couplings are dense, every single neuron is connected to every single neuron, you get oscillations, but you get kind of there is no notion of spatial locality, there is no patterns here. If we just do the same thing as we did before and we replace that with a convolution, suddenly you get waves in this oscillator network as well. And there's people like Bart Ermentrout have done a bunch of theory on this. Basically, you can do this transform and transform a real value sequence into a complex value sequence. We can visualize the approximate phase of these dynamics, as well as computing the velocity of the waves through the gradient of that phase. We can see at the beginning of training, there's nothing. Later through training, the model learns to propagate waves in order to solve these tasks. I'm not going to go into the details of that, it's not super relevant. But I do want to talk about what other types of things we can do with this general idea. So the first one was this like one-dimensional wave equation, the simplest possible thing. A more realistic wave equation is this Korteweg-de equation, the KdV equation, which is the model of waves and like surface water waves. And so this has a bunch of what are called soliton solutions. So that's these little bumps that travel and they can pass through each other without affecting each other's shape.
It's a nonlinear differential there, right?
Yeah, so there's this nonlinearity here. Oh, whoops, that's supposed to be an H. This H is supposed to be multiplied by this.
Oh, right, H times H, yeah.
And then you have this third order partial derivative here. So I implemented this in the same way with the wave RNN. You get much more interesting kind of wave dynamics. You can see there's waves of different velocities happening at the same time and kind of passing through each other. Unfortunately, right now the performance is like exactly the same as the other model. So I think potentially the wave dynamics are not the bottleneck on this data set specifically, but I think there are cool properties that we'll talk about later of like what these different types of equations might be able to do for us.
Has anyone looked into whether these are actually implementable optically?
I believe so. I'm not an expert on that, but people do.
Just a day or a university and I'll go do my research.
Okay, yeah, I do not have one. I think
Okay.
maybe some people at Intel were working on these types of like optics. They call it like physical reservoir computing is a lot of one of the terms, like using a physical system to do the computation. The cool thing about this is that it's much easier to train when we have it all simulated in a network, and you can do backpropagation through it and stuff like that. So the other cool thing is you can do all the finite difference stuff again and implement all of these spatial derivatives with finite difference methods. If you go on Wikipedia, these are literally the convolutional kernels that you can use to implement first, second, third derivatives over space and with different orders of accuracy. So it's like actually relatively trivial. And in one of the notebooks, this stuff is there. So you can write any equation you want to run it in an RNN. Another example of a cool one is this like these neural field models. So like Wilson-Cohen models. This one has two populations that are interacting with each other. But this again is a spatial convolution. This is written over continuous space, but you can discretize it. You put this into a way, there's the other notebook that's in that channel is this model exactly. Then you get really interesting kinds of dynamics. And these these equations are known to have really cool like energy minima and fixed point dynamics as well, where you can get these like bump solutions and you can get spiral waves. So you can get really cool solutions to these equations and all sorts of different equations, and you can implement this now in RNNs and train it to do things and see what happens. Unfortunately, again, still not performing that well. But the idea is, so before my time runs out here, talk about why I think this is not just a toy thing and why this is actually something that's relevant and people should maybe be interested in. This was one of the first state space model papers that they scaled for language, and they started testing it on language. They called it Hungry Hippos. They built this H3 block. It's a state space model form, but the point I'm going to emphasize here, this is the regular state space model that they had before, diagonal SSM. This is S4, if you've heard of that. What they did in this Hungry Hippos paper is they made this block where they first run this shift SSM, which is a state space model where I don't know the correct term for it, that A matrix or the hidden connectivity matrix is literally a shift matrix. And then they do a combination of that with the output of this kind of original diagonal model. So you think, okay, it's kind of a hacky thing. How did they come up with this? Nobody really knows. This block has been used ever since then. In every single one of these state space model architectures, and even in these new architectures like I'll show. And the intuition they give in this paper is exactly this kind of delay line type of intuition of wave dynamics. So one of the things that I'm interested in is like, can I replace this with other types of wave dynamics? This is really doing this kind of memory storage and allowing for comparison. So like I'll say, this is the H3 block. In this new Mamba paper, they keep the same thing. They do convolution over the hidden state dimensions, which is effectively this shift matrix. If you look at the XLSTM, which is the competitor to the state space models, this is from what's his name, Seth Horweitzer's group. They also have, they don't emphasize it, they have this convolution over the hidden state dimensions here. They call this a temporal convolution over the hidden state. This is basically exactly like this, our toplets hidden connectivity we had before. They have two different architectures. Both architectures, they have that component. This is a paper from DeepMind, where they also build these linear recurrent units. They also have this temporal convolution over one dimension over the hidden state. So
I understand the hidden state's a vector, and all this does is at every time step, it makes it move in one direction. It's one step, one unit, it just moves it along itself. Yeah. And each of these hidden state blocks, you have a bunch of them, right, that all move at the same speed, or they're trained to move at different speeds?
It's so they don't initialize it as this shift matrix. It's just a convolution. So it's just like this toplets matrix. But so in this paper, they started off initializing it as the shift, and then later papers they kept the same rough architecture, but then let it be freely trained. But my intuition is that it's doing basically the exact same thing. Yeah, I'm almost done. The cool thing about all of this is that you can accelerate this a lot. So this was actually the first paper where I would argue is like the first paper that's doing the thing that makes state space models so powerful. So it's from one of my friends, Eric, in 2018. And the idea is that if you have an equation that's written like this with two binary operators here, if this binary operator is associative and this one is semi-associative and this one distributes over these two, so abstract algebra, basically one thing that satisfies that is if this is a matrix vector product and if this is a matrix vector addition that satisfies these conditions. If that's satisfied, you can run what's called a parallel associative scan algorithm, and that allows you to do this equation over t time steps in log t time. So it does that by parallelizing sequence, basically you take pairs of inputs at a time and sum them, and you get this kind of logarithmic computation over the entire input sequence. So this is that.
It's because it's linear or
Because it's linear and associative,
associative means.
meaning that you can distribute, like it doesn't matter how you, or sorry, not distributive, yeah, associative meaning you can group your,
Parentheses.
right.
Question, can't you do something with the FFT here, it's the convolution?
Well, sorry,
Can you do something with the FFT since?
It's very similar to the-
Yeah, log in.
yeah, I believe so, and that also helps if this matrix is a convolution matrix, then you can do everything in Fourier space, and then it's a diagonal, and that's much faster as well.
Yeah, but I think the question is, you can do it, we can get the same speed up and do it.
Okay,
So,
I would believe that. But I think the thing is they don't necessarily do the convolution, they're doing kind of arbitrary matrices here. But basically what I'm saying is we can implement these wave models in a super scalable way that is logarithmic and time dependency. So you can process the input effectively kind of simultaneously. You don't have to do this recurrence, which is the slowest part. So this is my slide, it's an ode to John. Is it possible that these waves could be more than just a memory? I have a few examples. I don't know. I don't think I had time to go over all of them. But I think that maybe waves can do something like encode the geometry of the inputs that you're seeing. So this is like this hearing the shape of a drum example that people have talked about based on kind of the eigenmodes of the drum.
So that's an inverse problem, right?
Right. Yeah. Can you infer the shape of the drum just from the sounds that it?
The answer to that is no.
No.
No, that's the famous Marquette's paper.
Okay.
And there are so-called isospectral surfaces, that is to say, surfaces of different shapes that have exactly the same eigenspectrum.
Oh, that's
It's
actually
still a set of measure zero.
Sorry?
It's still a set of measure zero in the set of all surfaces, so it's kind of. It's just as a point.
We'll talk about that later.
It just depends what I think the point's cool.
You're all aficionados here, man.
Let's start a debate. That is kind of interesting. Maybe those can serve if. Okay, so if the brain is using waves to do some encoding of geometry, then maybe these examples can serve as adversarial examples to humans. It could be something you could test. I also have a previous paper where it's like arguing maybe waves can structure your neural representations. This was this neural wave machines paper. So learning symmetries of the input, learning sequences. And then also I have a crazy thing at the end, and maybe I'll skip to because it's the most fun. If anyone, yeah. I don't want to keep people here too late, so I'll skip over the hearing the shape of the drum, but I think it is cool, and I think there are examples of like how wave propagation within individual shapes in a network of coupled oscillators can be basically a function of that shape. And then by looking at the kind of the shape of that wave, you can tell something about the shape of that shape, if that makes sense. I can, if anyone has questions, we can talk after and I can let everyone else go to sleep. I'll also skip the neural wave machine stuff. I'll go into the crazy stuff just for fun. So this is a paper from 2013 that has 0 citations. And it's called relativistic conformal symmetry of neural field propagation in the brain. Basically, they argue this equation can describe neural dynamics in certain settings. Gamma is some damping coefficient function of distance between neurons and velocity of waves. This R is the distance. This is your kind of like field potential. This is your firing rate, so like input. Basically, this equation has certain invariances or equivariances to changes of coordinates. So this is what they mean by conformal symmetries. So if this is a scale transformation, if you change the time scale by some factor lambda, you also change the spatial scale by some factor lambda. You can imagine like the input to you is suddenly slowed down and twice as big or something like that. Your dynamics actually don't change in some crazy way. This equation doesn't change, it changes just based on some scalar factor, which is a function of the wave velocity, distance, and that lambda value. That's a really nice property if you have a neural network, that your dynamics aren't completely messed up if your scale changes. They just have an associated structured change to them. So this is what we call in like the equivariant deep learning literature, equivariant neural networks. This is equivariant to a scale change. They're also equivariant to conformal symmetry changes. So what is that? Crazy transformation here. Conformal transformation is a transformation that preserves local angles. So it's like preserving local geometry. So it preserves angles, but not size or distance. And basically, even with this crazy transformation, this is still some kind of scalar transformation of the dynamics. So my argument is, okay, if this is really an equation that approximately
Oh, wait a
governs.
second, now, if you look in the parenthesis, there's a t, time. It's not a scalar.
Right.
T, and that means that it's minus t, which means it's exponentially down.
Oh, true, okay, I hadn't,
So it's time line.
So there is some kind of variance there, but it's not the.
it is a weird transformation, yeah. I think the main thing that interested me about this was that if you have some symmetries in your kind of governing equations of dynamics here, potentially this can actually be useful for doing some type of computation. And I think waves have, or like these wave types of dynamics have a lot of these symmetries in them. And one of those is like time symmetries, and I think that's a reason why they're good at storing memories. Yeah.
There's actually some recent papers that have argued that grid cells emerge because of some conformal isometry constraints, and grid cells are like representations that are highly symmetric.
Is this the James Whittington stuff or?
There's a few of them.
Okay, interesting. I believe it. I'd be interested to see that.
Yeah, for those who don't know, these grid cells, and you know, place fields when there's only one location where a neuron fires in an environment. That's the hippocampus. In the entorhinal cortex, it's a hexagonal grid in the environment. And as the rat goes through the environment, it will hit each one of those peaks. It will fire bursts of spikes at regular intervals. The d distance is a hexagonal grid. So there's some kind of geometrical explanation for that. There has to be.
Yeah, I think some people are arguing like translation symmetry in space.
Yeah, that's something that preserved translation symmetry of long degrees would do it. Okay, it's late, but I guess we still have the time, so.